Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on the law of sines. Now, this is the second lesson in our chapter for applications of trigonometry, and this is actually a lesson that I went through in my classroom that I'm going to work through now with you so you can hopefully better understand how to apply the law of sines. So what we're going to cover in this lesson is how to determine the missing sides of an oblique triangle when given angle side angle as well as angle angle side. We're going to talk about how to determine the types of triangles given oblique triangles, also known as the ambiguous case. We're going to solve the missing measures using the ambiguous case. And then lastly, we're going to end up with finding the area of an oblique triangle. Now, you might not be familiar with the vocabulary of an oblique triangle, so that's what we're going to kind of discuss here, or at least to kind of get started. But the way that I kind of started my lesson is I just wanted to give my students a triangle that kind of looks like an equilateral triangle, but then just have them understand, like, how would you write the height? So basically, if we have a triangle, if we want to write the height, we're going to draw a perpendicular line. Now, again, we don't know that this is a perpendicular bisector. We just know that we have a line representing the height that can be perpendicular. But from there, we actually have two right angles. And actually, let me go back to my red here. So by doing that, though, by creating a perpendicular line, we have two right triangles. So from there, what I can do is I can write a trigonometric ratio, right? I can say the sine of A is height over opposite, and therefore I can solve for H. I could also say over here in this triangle, the sine of C is opposite over hypotenuse. I'm seeing the H. H is height, not hypotenuse. So opposite over hypotenuse, and I could solve for H as well. So what we did is we recognized here that H is equal to C times sine of A, as well as A times sine of C. Well, since H is equal to two different expressions, I can set those expressions equal to each other. And that's exactly what I did here. So I started this with C times the sine of A equals A times the sine of C. Now, obviously, to try to say, well, I have C's and A's, why don't we put them together? So I divided C on both sides and I divided an A on both sides. And what I got was this proportion, where sine of A divided by A is equal to the sine of C divided by C. And that is what we call our law of sines. Now, again, if we wanted to talk about B, that would also be proportional to these two ratios. All we need to do is just kind of rotate our triangle to its side and then find another height. But the important thing about the law of sines is this ratio of the sine of the angle to its corresponding side length is going to be proportional for all the angles and side lengths. So now that is going to be true for oblique triangles. It actually works for right triangles as well. But the reason why this is going to be helpful for us is because for right triangles, we have Pythagorean theorem as well as the trigonometric ratios, right? You can see that I could not use the trigonometric ratios until I created a perpendicular line. Then once I had a right angle, I could use my trigonometric ratios. So when we have an oblique triangle is basically just a triangle that does not contain a right angle. So there's two ways that we describe oblique triangles. We can describe them as an obtuse triangle. That means they have one right angle. Or we can call them an acute oblique triangle, meaning that they have all three acute angles. So we're going to use the law of sines to help us find the missing measures when we have oblique triangles. Again, absent of a right triangle or right angle. Now, the important thing to understand from the law of sines, though, is understanding the labeling of oblique triangles. So previously, when we looked at a right triangle, there's a couple different ways that we labeled right triangles, right? First of all, you have the famous a squared plus b squared equals c squared, right? Legs and hypotenuse. Then we went into trigonometric ratios, okay, where we basically were talking about given an angle theta, we're going to have the hypotenuse, the opposite, and the adjacent. So if you understood how to label right triangles this way, then you were good for right triangles. Now, oblique triangles, we get a little bit more exact, in meaning that we give our triangles, some labels or some letters like A, B, and C. And then the the side length that is opposing that angle or corresponding to that is going to be the lowercase angle. So if here's big A, that's going to be A. If this is big B, then this is going to be little b. And then the C's always get messed up because, you got to make sure you're doing a little c, not a big C, but that would be little c. Okay, so now again, not all triangles need to be written like A, B, and C. And obviously what you'll see through this lesson is I will be moving the angles around. But typically, unless I know that it's an obtuse oblique triangle, this is kind of like my go-to triangle, an acute triangle that looks like this and label it that way. However, you'll see again, I will deviate from this because I do not want students to be caught up in, oh, A has to be here or the triangle has to look like that, because that can be dangerous for students because that will start getting them mixed up once we started getting into some problems. All right, so I started the lesson off with just kind of working through a angle side angle. All right, so basically here's the triangle that the students were, or here's the information the students were given. You can see how I created my triangle, right? So I had A, B, and C, just like kind of how I said, I assume, that's what I start with. I don't have angle C, but I have side length C, which you can see is right in between the angles A and B. Now, the important thing when we're looking into the law of sines here is that we have to have a proportion. We have to have a ratio. And in this case, we don't have a ratio, right? You have to have an angle to its opposing side length, which we don't have here. So what I did was I could figure out C, right? If you have two angles, then you can figure out the third angle, right? The interior triangle angle sum theorem, right? All the angles of a triangle add up to 180. So what I did is I just quickly figured out what the value of C would be, which ended up being 37 degrees. And now I have a ratio. One thing I forgot to mention that I mentioned to my students, we have two proportions here, right? And again, this is equal for all three of these. Again, like you're only going to use obviously a proportion, a ratio equal to a ratio. You're not going to have all three of these set. But what's the difference between these? Why would I provide you with both of them? And the reason being is typically when we're solving for something, we do not want to be solving for something in the denominator. So when we want to solve for an angle, we're going to want to use this proportion because you can notice that our angles are inside of the numerator. However, if we're trying to find a side length, then we're going to want to use this proportion because the side lengths obviously are in the numerator. So quick little tip that I did not cover when I was going over there. All right, so now I have a proportion, right? You can see that I have side length C and angle C. So you can see that ratio right here. And then I'm either going to solve for A or B. It doesn't matter. You just really just kind of go with one. I show my work in here because for the next ones, I'm not going to show my work. I'm going to try to move through this a little bit quickly. But basically to solve for A, I just multiplied by the sine of 61 on both sides. And then this is what I basically plugged into my calculator. Now to do this chapter, you're going to want to make sure you have a scientific calculator or at least a graphing calculator. And since we're dealing with angles that are in degrees, you're going to want to make sure you're in degree mode. Now we're finding a side length. I told my students to round to the nearest thousandth, but obviously depending on the question, test, quiz, homework, that could always change. But if I don't mention how to round it, I said just to round it to the nearest thousandth. That might not be what your teacher wants or what you're used to. So you can just go ahead and adjust the answers as you need. But once I find this side length, well then I can just do the exact same proportion here to go ahead and solve for B. One thing I would recommend though is don't use B over sine of 82 equal to this new side length over sine of 61 because again, this is a rounded answer. You could use the exact answer, but again, it's never going to be exact. It's still always going to be an approximation. So it's always best to avoid using approximations in your calculator or to calculate answers when it is possible. So since I was provided or since I originally had this ratio 23 over sine of 37, you can see why I used that twice. All right. Okay, so let's go and do another problem here. Now, in this case, wait a minute. That's not a angle side angle. Oh yeah, it is an angle side angle. Jeez. So in this case, everything's kind of written a little bit differently, right? And that's okay. So what I'm going to do is I'm going to still draw the same triangle, but I'm just going to put B here, and I'll put C here, and I'll put A over here. Okay? You don't need to do it that way, but you could do it that way. Now, I recognize that here I have 110 degrees and 30 minutes. Well, just remember, 30 minutes is like half a degree, right? Just like 30 minutes is half of an hour. So to figure out the decimal version, you're just going to take, well, I have 30 minutes out of 60, right? Because 60 minutes would give you 1 degree, just like 60 minutes gives you an hour. But you don't have 60, you have 30 of them. So 30 divided by 60, hopefully you recognize here, is going to be 110.5 degrees. All right, so I'm just going to use the decimal version here. So 110.5 degrees. And then C is going to be 41. And then we don't know A, but we know this is going to be 5 meters. Okay, so now we have a measurement, and that's okay. We're just going to want to make sure when we give our final answer, all of our side lengths we're going to want to make sure are in meters. So therefore, let's go and find A. So that'd be 180 degrees minus 110.5 minus 41 degrees. And therefore, that's going to give me 39. I'm just going to type into my calculator, so therefore I don't make a mistake, a silly mistake, and then get the whole problem wrong. So I'm getting 28.5, which 60, 70 looks good. So let's say that's going to be 28. Okay, so that's going to equal 28.5. Okay, so I'm just going to erase that and just say, all right, A equals 28.5. All right, so now I have a proportion. So therefore, what I'm going to do is just either solve for B or C. It doesn't really matter. What I told my students to do in class is basically provide me with the equation, and then you can provide the answer. So they have the triangle. They showed me the equation, and then they gave me the answer. That's in degrees. And then the next one is just providing the ratio. So let's do C here. So I do C over the sine of 41 degrees is equal to 5 meters over 28.5 degrees. Okay, so then to go ahead and solve this, all I'm going to do is multiply a sine of 41 on both sides. So therefore, on my calculator, I'm going to type in a 5 times the sine of 41. That's not it. 5 times the sine of 41. And then I'm going to divide that by, the sine. I don't know why I didn't write that. Divide that by the sine of 28.5 degrees. So sine of 28.5. And that gives me a 6.87. So when I round that, let's see, round that to the nearest thousandth, that's actually going to be a 6.875. Okay. One thing also, just to kind of make sure that you're aware of, like a lot of times when students are typing these into the calculator, they're very prone to making a mistake. So always go back into your triangle and like make sure like the side length makes sense. Based on these triangles, like we should not get like, I don't know, maybe if I miss a decimal point, like 68 or 6,500 or, 0.2, those shouldn't be values based on the information we have for this triangle. So just make sure when you're calculating your answers, make sure everything kind of makes sense, because it's very easy to type something into a calculator incorrectly and then get the whole problem wrong. Right, so then the next ratio, let's use B. So I'll have B over the sine of 110.5 degrees is equal to, again, 5 meters over the sine of 28.5 degrees. All right, so now we're just going to do the same thing here. So I'm just going to do 5 times the sine of 110.5 and then divide that by the sine of 28.5. In this case, I get B is equal to 9.815. Okay, which makes sense. And again, that's going to be meters. And that's basically really all we need to do for those problems. So it's, if you don't have a ratio, when you're doing the law of sines, you got to make sure you have a ratio. If you don't have a ratio, look to see what you need to do to obtain a ratio. In this case, we just needed to subtract our other two angles from 180 to find our missing angle. There we could now find the ratio. Then the next example is actually if I actually was to give you a ratio. So in this case, we have A equals 46 degrees, C equals 61. So in this, and C equals 12. So when I kind of draw this, A, B, and C, you can see that I automatically already have a ratio. So therefore, I didn't need to do any extra work. And in this case, so I go ahead and, apply, set up my ratio, multiply it, I get A here. But now, once I find that, so I have that side length A. Well, to figure out B, I have no information here, right? So therefore, what I need to do in this case is subtract my A and my C from 180 to give me 73 degrees. And now I can go ahead and use the law of sines to find my missing side length, B. So let's go ahead and do another example like this. And I guess I'm making sure that I'm doing all the ones. I guess I gave my students, I didn't even think about that I gave myself all the ones with degrees, minutes, and seconds. So, all right, let's go ahead and get through this one. So again, draw the triangle to understand what it should look like. So let's call this one B. Let's call this one C. And then we'll have little c here. So this is going to be 12 inches. All right, now this is going to be 16. So let's see, B is going to be 16 plus 25 over 60. So let's go and figure out what that is. 16 plus 25 over 60. And that is going to be 16.416. Now that's going to be repeating. So what I'm going to do is rather than just like round that to, 0.417, I'm actually going to store that as an answer. So I'm going to store that as, let's see, alpha B. So on your calculator, most calculators for scientific are going to have a storing feature, and you can store them into the memory of the calculator. So I'm going to store this as alpha B because I don't want to round until the very, very end. Then I'll go ahead and calculate C. Now in this case, I'm going to have a 103 degrees plus 15 out of 60 here minutes plus 30 out of 3,600 seconds, right? Because there's 3,600 seconds in a degree, and therefore we only have 30 of them. So that is going to be the notation for degrees. So I'll do 103 plus 15 over 60 plus 30 divided by 3,600. And that is going to give me 103.2583. And it looks like, I don't know, that could be repeating as well. So what I'm going to do in that case is, again, store this answer. Okay, so when I'm storing something, what I'm going to do is I'm going to put brackets around that. Okay, so that's going to tell me it's now a stored answer. So I'm going to hit store alpha C. Okay, so now I have these two angles stored as alpha B and as alpha C. And I recognize here I have a ratio, right? So therefore, let's go ahead and find side length B. So therefore, I'll do B over the sine of alpha B. So I'm going to use those brackets to tell you that that it was stored. And then 12 divided by the sine of C. And again, if you want to know where that stored answer is, you can just look at the stored answer and say, oh, that's what it's equal to, or at least that's the rounded version. So in this case, I'll just do 12 times the sine of alpha B. And then I'll divide that by the sine of alpha C. 1,603. So alpha B, yep, alpha C. Okay, so in this case, I get B is equal to 3.48. That doesn't seem, sine alpha B. Yeah, okay. All right, so 3.4, I'm sorry, that's going to be 3.484. All right. And therefore, now I can find A. So A is going to be 180 degrees minus stored B minus stored C. So I'll do 180 degrees minus alpha B minus alpha C. And that's going to give me a 60.325. So it looks like that got rounded to 3 decimal places automatically, or at least got simplified to 3 decimal places. So therefore, I don't need to store that answer. 60.325. I'll just go ahead and write that in there. Obviously, if it kept on going or repeating decimal, then you'd want to store A as well. But in this case, I'm just going to have A. Oh, and this is in inches, isn't it? So A over the sine of 60.325. is equal to, and let's again use 12 over sine of C. So 12 over the sine of C. So in this case, I'll just do 12 times the sine of 60.325 divided by, that's a stored C, the sine of alpha C. And I get 10.71. All right, so A is going to equal 10.712 inches. So you can see it's not really, obviously this triangle is not really drawn to scale, obviously because we have a big obtuse angle, and you can see that this measurement is going to be a lot smaller than the other ones. But again, still you can kind of see these measurements would make, some sense if we were to kind of maybe rescale or redraw the triangle. All right. So now we kind of got our feet wet with the understanding the law of sines. Now let's kind of get into the word problems. So the word problems for law of sines was basically, again, what we want to do is draw the picture, set up the triangle. Now in this case, we're looking for the oblique triangle, and then we're going to look for the ratio. And if we don't have enough information for the ratio, we need to be able to see what can we do to create a ratio. So this word problem says 2 observers, 1.6 miles apart, see a hot air balloon between them in the air. So let's go ahead and immediately draw 2 observers. So we have observer and observer. And they see a balloon. So I'm just going to, there you go, draw balloon. Okay. Hot air balloon. Now it's in between them. Now it looks like we don't know if it's directly in between them. It does not say. All it says that there are angles of elevation of 36 degrees and 28 degrees. And I think that hopefully is a kind of a giveaway that if it was directly in between them, the angles of elevations would not be the same. So therefore, this is going to be 36 degrees. This is 28 degrees. And how far are they apart? Oh, it doesn't matter. Oh, they're 1.6 miles apart. So they're 1.6 miles apart, and we need to figure out the height. So again, we want to label what we are looking for. Okay, so we're looking for the height. Now, the problem is, based on this information, I need to create a ratio. I have no idea how long this is, no idea how long this is, and I have this length. So if I have this length, is there anything I can do to figure out this angle, right? Because I have to get a ratio. Well, thankfully, I already have 2 sides of my triangle, right? Or 2 angles, I'm sorry, of my triangle, 36 and 28. So I'm just going to go ahead and figure this to be 180 degrees minus 36 degrees minus 28 degrees. So I'll do 180 minus 36 minus 28. And that's going to give me 116. All right. So if that angle is 116 degrees, now I have a ratio. Now, again, that does not help me with the height, but it's important for me to understand the height is actually part of a right triangle. So let me draw one more triangle here. And let's just do this one. So if I have 36 degrees, I don't know what this length is. You do not want to make this assumption that it's halfway in between because they don't have the same angles of elevation. So that doesn't make sense. We don't know the height. That's what we're trying to find. Now, the only other side length is this. Now, this is the side length of an oblique triangle. Well, if I already have a ratio, I can find that other side using the law of sines. So what I'm going to do is I'm going to say, all right, 1.6, let's call this one A, and let's call this one B. That means this is going to be little b, right? So I can say 1.6 over the sine of 116 degrees is going to be equal to B over the sine of 28 degrees. Okay. So now you're just going to multiply, 1.6 times the sine of 28 and then divide that by the sine of 116. And when doing that, that's not right. 1.6 miles. Oh, what am I doing? That's not hundreds. That's 116. What am I doing? Yeah. That's 1.6. 1.6 over 100 sine 16 is equal to B over that. Oh, yeah, I guess that is right. That is right. That's fine. Okay, so B is equal to 0.8357. Now, or 6, yeah, because I'm going to round to the nearest thousandth. However, I'm going to round this. You can see this is multiple digits, so I'm going to store this as an answer, okay? So I'm going to now label this as a stored answer B because I don't want to round until the very end. So I'm going to hit store, and then I'm going to just take that as alpha B. But now, if you look at this triangle, you have sine of 36 degrees as opposite over hypotenuse, right? So you can say sine of 36 degrees is equal to H over stored answer B. So then all you got to do to find H is just going to be stored answer B times the sine of 36 degrees. So then I'm just going to type in the sine of 36, close the parenthesis, times alpha B. And in this case, I'm getting H is going to equal 0.491. And that's going to be in miles. right? It makes about sense. Like this is 1.6 and that's, 0.8. Then this height is obviously going to be a little bit shorter. So 0.49 makes sense. It's not like 5,000 or like 0.0003. So you can see here how we had to create our ratio, but then also just by solving the law of sines isn't our answer. Like we need to make sure we understand the height of the balloon, right? Which I should also define the variable, which I forgot to. H equals the height of the balloon. Okay, because I make sure I solved it, but I didn't define the variable. All right, next problem. The course of a boat starts as point A and starts at point A, and let's fix that. And proceeds in the direction of south 53 degrees east for some distance to point B. Then in the direction of south 39 degrees west to point C, where it lies 8 miles directly south of point A. What is the total distance of the boat traveled? All right, so whenever we have a word problem or we have a bearing, I always tell students to draw the compass heading. So we have this, it's going to be south 53 degrees east. So I'm just going to draw this compass heading. I do a nice one there. I did it. Okay, so we have north, east, south, west. All right, so it's going to go south 53 degrees east for some distance to point B. So again, it starts at A. And then let's just go, I don't know, to here. And then let's call this B. Then it says, then it changes direction to south 39 degrees west to point C, which lies directly south of point A. Okay, so we're going to do another compass heading. So, again, north, east, southwest. And then point C, they said, is directly south of A. So we're going to call this C. And now you can see we have our triangle. All right. So let's kind of go through our angles. So we did south 53 degrees east. So there's that angle. And then this one is south 39 degrees west. Okay. And the only thing we know that the distance from point C to point A is going to be 8 miles. All right. So again, we have an issue because we do not have a ratio, right? We have one angle and we have one side length, but we don't have a ratio. Now, the important thing is whenever you have a compass heading, we know that those create parallel lines, right? North-south is parallel with north-south. So therefore, what I'm going to do in this case is I'm going to look at my parallel lined relationships, right? Remember parallel lines in a transversal, alternate interior angles, corresponding angles, alternate exterior angles. All of those can come about. So if these two lines are parallel and I have 53 degrees here, well, alternating on the other side of this transversal makes that 53 degrees. Now, again, that's not inside the triangle, but I recognize that that could still be kind of helpful. Now, the other thing you could do is I can say, well, then if that's 39, then this is 39, right? And then, so yeah, you could use this as like complementary angles. Like if that's 39, then you know that this has to be 51 degrees, right? But you could also just say, well, if this is 39, this is 53, I can figure out what those angles are, right? I don't need to really do any more. So the nice thing is just knowing that you have these as alternate interior angles, you can now figure out that angle. And again, we need that angle because that's going to be opposing to our 8 miles. So let's see, we're just going to do 180 degrees minus 53 minus 39. So I'll just, again, type in my calculator here. Just because now I'm dependent on my calculator like all my students. Once we give them, we're like, oh yeah, there it is. So that's going to be 88 degrees. Okay. All right, so now I have a ratio. And again, we basically need to be able to solve for these two lengths. Now, we could call this little c and then call this one little a. Right? So let's go ahead and do that. Let's solve for C here first. So we'll do C over the sine of 39 degrees is equal to 8 over the sine of 88 degrees. And now we'll just go ahead and multiply by the sine of 39 on both sides. So I'll do 8 times the sine of 39 degrees, and then I'll divide that by the sine of 88. And that's going to give me 5.038. And again, remember that's in miles. And then we'll do A over the sine of 53 degrees is equal to 8 over the sine of 88. Okay, so we'll just multiply by the sine of 53 again. So that's going to be 8 times the sine of 53. And then divide that by the sine of 88. And therefore, A is equal to 6.393. And again, remember that's in miles. Okay, so there you go, ladies and gentlemen. That's basically the gist of the law of sines when we're dealing with a ratio, or at least a triangle that we can create a ratio. Now we're going to move into the lovely situation where we cannot confirm if we have all the information needed to identify what the triangle would be. And that is what we call the ambiguous case. So the ambiguous case is if we have two sides and a non-included angle are given, which is also called the side-side angle triangle. 3 situations can occur. So we can have no triangle exists, which is this one. We could have a right triangle exist, which would be that one. We could have 2 triangles exist, which is usually the confusing one. Or we could have the 1 triangle exists. So the first 2 examples, usually people, once we kind of work through this, they understand it. Really the difficult one, is it this 1 triangle case or this 2 triangle case? So what I do with my students is I had a conversation. I said, all right, guys, let's look at this document. And let's say, how does really the height of the triangle, how does that like relate here to the type of triangle that we have, right? If there's no triangle, how does the height of this proposal triangle like relate to it, right? Like here would be the height, right? How does the side length relate to the height? Same thing here. How does H relate to A? Or here, or here. And the point that we wanted to see was that when the opposing side, this A, was shorter than the height, no triangle existed. When H is equal to A, you can see that 1 right triangle exists. The one thing that we got to make this confusing difference here is when A is larger than H, which is not true for these two. So when A is larger than H, you either have 1 or you have 2 triangles. So what is the difference between these? Well, the difference is, in this case, you can see that A is larger than B. In this case, you can see that A is smaller than B. So what I did is I kind of summarized all of this into some cases. All right. And basically what we want to do when we're trying to identify the type of triangle we have for the ambiguous case is to find the height. Now you might recognize that formula for the height because that is exactly what we did at the beginning of class. H equals B times sine of A, right? If you create a nice little right triangle here. Now I did label the triangle differently than what is shown here. I did have B up here and C over here, but we're going to stick with this being angle B. So therefore that's little b. But if you're given this information here, you can identify that the height of this triangle is going to be the sine of A is opposite over hypotenuse. And when you solve for H, you get H equals B times sine of A. The way that I have this memorized is when you have, angle, side, side, right? Angle, side, side. Whatever angle you have that ratio with, your corresponding angle and the side, then that's going to be your corresponding angle. This would be your included corresponding side. This would be like your included side. So you're always going to take your included side times the sine of your angle. Now, I always hate writing it like that, so I'm just going to write it because I know some people are still like, oh, side, side, angle, side, side, angle. Whatever your angle is, times that nearest side. But again, you can kind of see this relationship. Once you find the height, right, just relate it to A, okay? Now again, the letters is not what's important. What's important is understanding the side length, how it relates to that other side. And again, really the one that our students really get confused here is when A is larger than H, because you need to determine is A bigger than B or less than B. And again, this is when A is acute. So if you have A is obtuse, it actually gets even easier. When A is obtuse, A has to be small. If A is smaller than or equal to B, then no triangle exists. And if A is larger than B, then 1 triangle is going to exist. So yeah, so that's just kind of important to understand. And again, like that makes sense. Like, I don't know why I didn't do this as a larger triangle, like an obtuse triangle. I should have redrawn that. So like if here's A, right? Here's B, or sorry, let's put that as B is over here. So therefore this is A and this would be little b, right? So you have angle, side, side. So if A is larger than B, then you can see one triangle exists. But if this ends up being shorter and this is an obtuse angle, like you're not going to have a triangle, right? If this was like shorter than B, no triangle will exist. Or even if it was exactly the same measure as B, there would be no triangle exist because therefore then it'd have to be a right triangle. And if this is obtuse, then it obviously can't be both. All right, so one of the types of problems we'll talk about is the ambiguous case, is how to determine if the measure is 1, 2, or no triangles. I will be a little bit more detailed in this case as far as identifying if it's a right triangle as well. So the main thing I like to do is just kind of draw the picture of the triangle. So I'll have C, so we'll have 75, this is going to be 10, and this is going to be 12. So then I like to find the height, which in this case is going to be 12 times the sine of 75 degrees. And let's see, that's going to be 12 times the sine of 75. That equals 11.6. Okay, so you can see that 10 is shorter than the height. So therefore, no triangle exists. This next one, you can see it's obtuse, so I don't need to worry about the oblique triangle happening, but I know that this is going to be 148 degrees right there. And therefore that's 8, and that's going to be 16 or 25. Again, if you remember, this triangle doesn't make sense how it's written, right? If this is your opposing side and that's smaller than that side, there's no way a triangle is going to exist. So again, this is another example of no triangle exists. On the next one, let's go and draw this here. So this one would be B. Therefore, this is 9.9, and this is 8.1. So let's go and figure out the height. So I know this is bigger than that one, so I know it's not going to be 2 triangles or 1 triangle, actually. Or actually, I'm sorry, we know it's not going to be 2 triangles, and it should be 1 triangle. Let's just go ahead and confirm. So let's go and figure out the height. So that's going to be 8.1 times the sine of 63 degrees. So 8.1 times the sine of 63, and that's going to equal 7.2. Okay, so again, since the opposite side here is larger than the height, we know a triangle exists, and since it's larger than the other side, you cannot create more than 1 triangle, so therefore that's going to be 1. The next example here, we have another acute angle. So let's go and draw this. Oh, I didn't do those. So here I'm going to have 12 degrees, okay? And then my opposing side is 28. And then this one is going to be 8. BB 8.1. Yeah. All right, so now I'm just going to do, so obviously it's going to be either be 1 or none. So let's go and figure out the height. So that's going to be, that's going to be 8 times the sine of 12 degrees. So I'll do 8 times the sine of 12 degrees. That's going to be 1.6, which is obviously bigger. However, that cannot rotate into both of them. So therefore, there's only going to be 1 case that's going to work in that one. This next one, we're going to want to relate this to our decimal form. So I'm going to do 23 plus 34 divided by 60. Oops. Plus 41 divided by 3,600. And that gives me 23.578. Now I'm going to go ahead and store this. Okay, just so I have use an exact answer. So I'm going to say store as alpha A. And then my triangle is going to look here let's say, so that's going to be 2, and that's going to be 5, and this is going to be, 23 degrees roughly. So let's go and find our height. So h is equal to 5 times the sine of 23 degrees. So I'll do 5 times the sine of alpha a. Actually, let's use the stored a. So we know that we're using the stored answer. And when I do that, I get 1.99999, and I think that's going to be just a rounding error. You can see that that's actually exactly the same as equal to 2. So therefore, this is going to turn us into a right triangle. 3.2, C is 95 degrees, so let's go ahead and draw a right triangle here. All right, so there's going to be my C. This would be 10, and this is going to be 3.2. So again, once we know that this is a obtuse triangle and this side's gonna be larger than that side, we know it's going to be 1. Now I'm looking at this and I say, uh-oh, there's a mistake here. Now, obviously that's not gonna be my second case. This was supposed to be my 2 case, so I think I made a mistake. I need to change this up. If my height here is 7.2, I think this should not be larger because then we know it's gonna be 1 case. I think I wanted this to be 7.9. So if that's 7.9, and I'm sorry, I'm going to go back and change. I thought I worked all these out. Okay, but now you can see 7.9 is larger than my height, so therefore we know a triangle is going to exist, but it's smaller than my other side, so therefore this was supposed to be my 2-case solution. So sorry about that, but I'm going to go and change the answers there. Okay, then on to the last one, which is the ambiguous case, which I used to teach a lot, but it takes so long to be able to do it. And so what I did is I really didn't kind of go through an example. I wanted to provide at least one example, so therefore students can see what I'm doing, but I don't really want to cover any more than that. So basically we have our side lengths, right? You create your triangle. The problem is when you figure out the height, it's 8.4. Now 8.4, the opposing side length is larger than 8.4, but it's shorter than the adjacent side, right? So therefore you don't know if 10 should look like that or like that. Right? So it has to be 2 of the 2 cases. You either have case 1 or you have case 2, the acute triangle or the obtuse triangle. There's not enough information for you to determine which one is which. So the first thing you do is just kind of go off of, let's just assume it's the acute triangle. So therefore you create your ratio. Now again, notice you're finding the angle B, right? So when you go ahead and create your proportion, you got to make sure you're going to want to put the angle, the sine of your angle B in the numerator, and you go ahead and solve for that. Then you're going to go and solve. You're going to use your inverse operation, and therefore you're going to get angle B right there. Ends up being 57.409. Then you can subtract that from 180 or subtract your angle, 37, plus your B to be able to find your last angle, which is C. Notice I'm putting the brackets around everything because I'm storing everything in my calculator. So the other thing that's difficult about this is there's just a lot of storing. Okay, so once you find angle B, right, you already have angle A, and then you find angle B, so you're subtracting them from 180 to find angle C. And then again, you create your proportion to find side length C. Notice how I use the proportion where my side lengths are now in the numerator. Then we got to go and figure out case 2, which is the obtuse angle. Now again, we don't know if it's the acute, if it's case 1 or case 2, like we don't have enough information. So we got to look at what is the relationship between B and B2. Well, the relationship between B and B2 are they are supplementary angles, meaning they add up to 180. So that means I already found B. If I want to find B2, which would be the obtuse angle here, all I'm going to do is I'm going to take 180, subtract it from B, which again is still stored in my calculator. And that gives me an obtuse angle, right? Right there, 122 degrees. And then I ended up storing that as a different variable D. Now, again, you could replace that with B since you're already done with case 1. But just to keep things in case I wanted to go back to them, I stored it as a different variable D. That's why you can see B2 and D. You can see it's all defined here though. Well, now I have B2 and then I already had A. So then I can take those 2 answers, subtract them from 180. So I do 180 minus C minus B2, which is stored as D. And that gives me another acute angle, 20.4, which I stored as E. Then the last thing we need to do is find the third side, which is going to be C over sine of E equals 10 over sine of 37. And therefore your C is going to equal 5.795. Boom. Okay, so now let's actually go through an ambiguous case to be able to find the missing measures of both triangles. So the first thing we're going to want to do is actually draw the triangle to kind of see what it's going to look like. So we have, here is our angle B, and then this side length is going to be 7, and this is going to be 10.5. All right. Now, again, if we didn't know this was the ambiguous case, we could always check out the height. And to do that, I would just do 10.5 times the sine of 35 degrees plus 6 minutes divided by 60. And that's going to give me 6.037. I don't need to find the height, but what I can recognize here is that this side length is larger than the height, but it's smaller than this case. So again, to like kind of visualize this, we have this angle is defined, and we know that this side length is defined as well as this side is defined, but we don't have this angle defined, nor do we have these two angles defined. So that's why we don't have enough information. We don't know, is this an obtuse angle or an acute angle? Now, again, these are going to represent here C. So we could call this C1, and then we could call this angle C2, right? So therefore, this is going to be B. Now, again, last thing is notice how I created the triangle. I always create it with a angle side, side. All right. I always create the ambiguous case just like that. And then I just move around the letters as I need. Now, the first important thing is to just find case 1, just like we did before. So I'm just going to do case 1 right here. So it's usually easiest just to, pick your side and say, all right, let's just assume that this is an acute triangle, an acute oblique triangle, and therefore we can just solve from there. So what I'm going to do is we're going to find C1 here. And so what I'm going to do is say, all right, let's go ahead and find C. So I know I have, now again, we're going to looking for the angle, right? So I'm going to say the sine of C, sine of C1 over 10.5 is going to equal to the sine of 35. Now again, what is 6 minutes out of 60? So 6 divided by 60, that's going to be 0.1, right? Yeah, 0.1. Okay. So I can just say that's 35.1 degrees over 7, right? That's 6 minutes over 60 is equal to 0.1. All right. So now what I'll do is I'll go ahead and solve for C1. So I'll just say multiply. So I'll do 10.5 times the sine of 35.1. And then I'm going to divide that by 7. Now, again, remember, when you're trying to find for the angle, you need to use inverse sine, right? Because it doesn't make sense here. Here's actually really important to talk about. So the sine of C1 is equal to 0.86 250787881. And the reason why I'm writing this down is because I want students to be able to understand, like, that's not the angle. That angle does not make sense. That's way too small of an angle. If you already have one angle, it's going to be 35 degrees. Like, yes, obviously it's possible, but it's very unlikely. And you need to understand, though, we haven't solved for C. We solved for the sine of C. So again, C1 is going to be the sine inverse. Now I have this in my calculator, so I'm just going to use the answer feature. So you look on your calculator, look for that ANS, and I'm just going to do sine inverse of the last answer. And that's going to give me a 59.5999. So let's say C1 is equal to 59.599343, which I'm going to store as equal to C. So I'm going to write that's equal to C, and I'm going to store that in my calculator because I don't want to round it until the very end. So I'm going to store this as alpha C. Okay. Now I have two angles, right? So if I already have C, which we're calling C1, I can be able to figure out what is my, what in this case is going to be my A1. So A1 is just going to be 180 degrees minus, A1 is going to be 180 degrees minus 35.1 degrees minus stored C. Okay, so then I'll just do 180 minus 35.1 minus my stored answer C. So I'll do alpha C, and that gives me 85.300 or 01, which is rounded. So I'm going to store that as alpha A. Now again, I already have, since I now have A and C, I already have C and B, I just need to find A. So now all I'm going to do is I'm going to say, all right, well then A over the sine of A, stored A, is going to equal 7 over the sine of 35.1. And then for now, I'm just going to do 7 times the sine of alpha A, which did I not save that? I didn't. Crap. Okay, so store that answer. So I'm going to store this as alpha A. I said it, but I actually didn't do it. So now that's stored as alpha A. And now, so I'll do 7 times the sine of alpha A. And then I'll divide that by the sine of 31.5. Okay, so therefore A gives me 13.352. Okay, so that is case number 1. Now, again, that is for C1. That is assuming it's a acute triangle. But what about if it's an obtuse triangle? So that'd be case 2. So then we need to understand is what is the relationship here between C2 and C1? Well, again, they're supplementary angles. So C2 is equal to 180 degrees minus C1. So all I'm going to do is do 180 minus C, which I calculated here, which I stored as alpha C. So that's going to be alpha C. Writing that in there, I'm going to get 120.4006. But again, I don't want to round this, right? I'm going to want to store this. So I'm going to store this as a new C. So I'm going to store this as alpha C. So I'm going to do store as alpha C. All right, so that's replacing my old C from the previous problem. But now I have 2 angles, therefore I can find a new angle, A, right? So A2 is now going to be 180 degrees minus my new C minus my B, which is going to be 35.1. Now again, remember, actually, yeah, we see that you can see that C2 is obtuse, right? Which we needed. We knew it had to be an obtuse angle. So then I'll do 180 minus alpha C. Did I store that? I did. So I'll do this as stored as alpha C minus 35.1. Now again, if my original A was this big and now it's getting this big, it should be smaller than 85.1 degrees. And I end up getting 24.45. So again, that is going to be smaller. So 24.499. And again, I'm just going to store that as alpha A. So I'll just store that as, so I'll do store as alpha A. All right. Now, again, we have 2 side lengths. I need to be able to figure out the other side length of A. So to be able to do that, all I'm simply going to do now is create one more ratio, and that's going to be with A. So I will have, let's see, where do I have anything with A? So I have angle, so I'll have A over the side of my new A is equal to, let's do B with sine of B. So I'll do 7 over the sine of 35.1 degrees. Now all I'm going to do is take 7 times the sine of alpha A and then divide that by the sine of 35.1. And in this case, now I get A is going to equal a 5.08. And again, that should be smaller than my other A, right? Which is a 13, because A originally was this big. Now it got shrunk down to this big. So you can see how it go ahead and make sense. All right, last but not least here is we're going to talk about the area of a triangle. Now, again, remember when you have a triangle, like, you know, good old days, area equals base, height. So area equals 1/2 base times height. Well, what if you don't have a right triangle? Or what if you don't have it as a base, or you don't know the height? Like, for instance, what if you have an oblique triangle? Well, again, if we think about this, we still need to figure out the base, right? But we've got to figure out the height. Now, if we know an angle, for instance, A, then we can say the height is going to be, remember, the height of a triangle, let's call this, here, I'm just going to call this C. This be B and this be A. Remember, I have all this room down here and I'm not using this. So that's what we've previously learned, right? But if you have an oblique triangle, let's actually just redo this. So if you have an oblique triangle now, and let's call this A, let's call this B, and let's call this C. Well, if you need to find the height, right? What we talked about at the beginning of class today was that you can find a relationship of the height based on your opposing side lengths. So therefore, you can see that little c is the base of this triangle, and the height is going to be the included side times the sine of A. So you could say B times the sine of A is equal to height. So therefore the area is equal to 1/2 base, which in this case is C, times B sine of A. And again, if we keep on rotating our triangle, you can see how we would get different ratios for each one of those. So you can see here, that is my equation right there. The B and C are just flopped. But you could work on those for each and every one of them. So that's all we're going to do when finding the area. We're just going to find the area of these following two triangles. So in this case, we have our angle and we have our B and our C. So very good here. So that means all I'm going to do in this case is, let's just draw the triangle though, just to make sure we have everything. So here's A, that's 16, and that's 18. So we have area equals 1/2 B times C times the sine of A. And again, A is going to be 5 degrees and 100 seconds. So I can just type that in the calculator. I don't need to evaluate that. So I'll just do 1/2. So this is going to be times 18 times 16 times the sine of 35 degrees plus 5 over 60 plus 100 over 3600. Okay, so we do 0.5 times 18 times 16 times the sine of 35 plus 5 divided by 60 plus 100 divided by 3600. And I'll close the parenthesis there. And I am going to get an area of 82.824. Which seems relatively, depending on this height, because if I had the height, which would be, I don't even know what that sine is. So sine of 35, if you're doing 16, so that'd be 18 times the sine of 35 roughly. So it's giving you a height of 10, and then it's be 1/2. So yeah, seems like 180. Seems like that pretty much works. It seems in reason. Just remember, if you're using units, that's going to be your unit squared. For next example, I noticed that I have two angles. Well, that's kind of an issue because I need to have I need to have two side lengths in one angle. So I'll draw my triangle. Here's 10 degrees. Let's call this big B. This will be little b. And let's call this big C. And therefore, I need to find little c. So the problem is I don't have enough information. However, I could kind of quickly, easily figure out what B would be. 180 degrees minus 10 minus 95 degrees. So I could do 180 minus 10 minus 95 degrees. That's going to give me 75 degrees. Now that I have this as 75 degrees, what I can do now is create a ratio. So now I can say that 3.2 over the sine of 75 is equal to, let's go ahead and find, doesn't really matter which one. You're either going to want to solve for C or for A. You just need two of them. So therefore, I'll just solve for A. So A over the sine of 10 degrees. So do 3.2 times the sine of 10 degrees divided by the sine of 75 degrees. Whew. And that's going to give me A equals a 0.575. And then when I go ahead and plug that into my calculator, I have 1/2 times A times B, and then we'll do times the sine of C. So I'll just type all of that into my calculator. So I'll do 0.5 times that last answer, which was my A. So I'm not going to store that. I'm going to just use my last answer. And then times that times my B, which is 3.2. And then times that by the sine of C, which is 95 degrees. And I get 0.91. And therefore, based on that information, looks like that would relatively work. So there you go, ladies and gentlemen. That is the law of sines. You can see that we covered the area of oblique triangles. We talked about how to identify the ambiguous case, find all the missing measures, how to label 1, 2, or no triangle, as well as determine if it's a right triangle. Then we talked about obviously just understanding that ambiguous case, as well as looking into some word problems and finding the missing measures using angle, angle, side, as well as the angle, side, angle. So therefore, I hope you enjoyed, and I look forward to seeing you on the next video. Cheers.